Hi, welcome to a new section of this course, Being Lazy, Queues and deques. In this section you'll learn about functional deques. We'll take a quick look at how deques are implemented imperatively. Next we'll look at amortization, and we'll play a bit with stream, that is Scala's lazy lists. Finally, we'll implement deques using similar techniques. Now we move on to the first video of this section that deals with imperative implementations and amortization. In this video, we'll use a doubly linked list, allocate a new array, and double the size of the current array. After this, we'll copy all the elements from the current array to the new array, and then make new array the current array. Implementing a deque is simple in the imperative world. We could use a doubly linked list that will give us big O of 1 push and pop at both ends. Have a look at this figure. If we keep track of the first and last elements, adding or removing elements at either end would just be a matter of twiddling a few pointers. Of course, we cannot use this model as we never ever mutate a data structure in place. What about efficiency then? Hang on, we'll soon see how amortization and laziness help us design an efficient deque algorithm. To better understand the concept of amortization, let's look at a dynamic array. This is an array that would grow if there was no space to add a new element. We could do this with the steps listed here. First, we allocate a new double array the size of the current array, and then copy all the elements from the current array to the new array. Lastly, we make the new array the current array. Here is a simple run of the algorithm depicted pictorially. This allocation and copying obviously incur big O of n cost once in a while. If most of the elements incur a big O of 1 cost, we should be fine though. If you continue to trace the growth of this array, you'll soon realize that the allocate and copy operations occur less frequently as the number of elements grow. Most of the insert operations would have big O of 1 complexity. In other words, an insertion would complete in amortized constant time. Consider our queue implementation using two lists from the previous section. When the out list becomes empty, we substitute it with the reversed in list. Or rather, we could say, if the out list is empty, the in list has to be empty. That is, the entire queue is empty. During the pivot step, the invariant is temporarily violated and then restored. To jog your memory, let's write the code. Define the FIFO class with outList and inList. Next, define check method as Boolean. We create the case clauses. Declare the required method. Note the use of the require method to make sure the invariant always holds. We use a method called check. This method, in turn, uses pattern matching to check both the lists. Here's the first clause. This clause matches when the out list is empty and the in list is non-empty, that is, it has at least one element. We know this violates our invariant and the object construction is aborted as a result. This makes it impossible to end up in a state with a queue that has elements inserted but no ability to pop them out. This is an anomaly that the assertion helps us catch. So, our FIFO class is now defined. Now let's define the pop method with a FIFO queue. Let's match the queue and create the case clauses. We throw an illegal argument exception. Write the second case where we use the copy method. Similarly, write the third case clause. Note the second case clause where the substitution happens. When we have a large number of insertions, reversing the in list would possibly incur big O of n cost. This would happen once in a while, but that would still be something at least. So, most of our push and pop operations would be big O of 1. Given the occasional in list reversal, that could be big O of n. This is the concept of amortization, where the occasional cost of reversal is paid off by having big O of 1 push and pop operations. We may have an occasional expensive operation. However, the overall pop cost will be big O of 1. In this video, we've learned about imperative implementations and amortization.